First of all, I would very much like to mention that Alex Kontorovich is a brilliant musician. He graduated magna cum laude from Princeton Mathematics and obtained his PhD at the Columbia University. He worked at Yale, at Stony Brook, at Brown Universities. He is currently professor at Rutgers University Mathematics Department, also editor-in-chief at Experimental Physics, scientific board member at Quantum Magazine. He is distinguished visiting professor for the public dissemination of mathematics at National Museum of Mathematics. He is in the program committee of AMS Eastern Section. Some of his awards are Simons Foundation Fellow, Elected Fellow of AMS, Kavli Fellow of US National Academy of Science, and many others. He gave over 200 lectures since 2007. You can watch some of these amazing lectures on YouTube, actually. Some of his research interests are as follows: analytic number theory, harmonic analysis, representation and L functions, hyperbolic geometry and spectral theory, ergodic theory, and many others. Also, there is an inspirational interview with him at Strogas Joy of X podcast on the absolute truth of pure mathematics, which I recommend to our audience. Well, we are so lucky to have him here today. There is so much things to say. In a nutshell, get ready for deep insights. Okay, thank you.
Thank you very much for that kind introduction, and thanks for the invitation. It's a great pleasure for me to speak with you today. I'd rather it be in person. I've never been to Turkey, and I would love to go. I was supposed to go another time. There was a meeting of the what was it? Not the European Mathematical Society. It was Journée Arithmétique, which is a semi-annual meeting for number theorists, which took place in Turkey last year, and I was hoping to go but didn't get a chance. So another time I hope would be great. Please stop me at any time. I just want to have some casual conversation and tell you a little bit about some interactions between, as I understand it, most of you are physicists, is that right? So I will try to keep the number theory light-ish, but I want to at least give some illustrative examples of, at least in one setting, maybe more if we have time, of the fruitful interactions between our two subjects, yours and mine. So I'm traditionally a number theorist, although I very much admire mathematical physics. And so I want to tell you a little story. Okay, so as much as you can, please interrupt, please ask questions. I don't want to just talk to myself into the void, so stop me anytime. So this is a wonderful picture that I just saw actually yesterday, a little movie that was going around on the internet, where an artist, a Japanese artist, started with 4 little clumps of sand in the on a table, on a certain circular table. And he started to, he took like a, well, it's sort of like a violin bow. And if you bow the side of the table vibrates. And depending on, and you can put your finger at certain positions in the table to sort of force a harmonic that has a nodal region at that particular point on the table. And when you do, and you bow, so you can see sort of, there's his finger right there on the side of the table. And with his other hand, he's bowing he's stimulating the table, and he gets all of these beautiful harmonics. So what you're really seeing is the nodal domains of those harmonics. The places where the table is fluctuating, the sand is getting spread all around, and the places where the harmonic isn't doing anything, that's where the sand will accumulate. And so there's this amazing he has amazing control of this instrument, the table, with no sound. The only thing you see is that he didn't take his hand and spread it out or anything. I wish I had a better way of showing you this video, but anyway, so these are well known. These have been studied for hundreds of years. They're often referred to as Chladni patterns. Chladni was maybe among the first to document them in some serious way. So the question is, how did these things form? Well, again, as we just said, they are the nodal regions of various eigenstates of the Laplacian, eigenvalues of the Laplace operator on this manifold. So let's say in general you're given some surface, which for now you can just think of as a subset of the plane, some nice open domain connected. And when we're interested in solving the differential equation, Laplacian phi equals lambda phi. Okay, so we're looking for eigenvalues of the Laplace operator. The Laplace operator acts on square integrable functions on the manifold. So far, so good? Any questions? So this is kind of where you might start to think about such things. And every time you have an eigenfunction, you can normalize it so that its L2 norm is 1. And that gives rise to a probability measure. So what do you do if you have a measurable set A? What you do is you just integrate A over, you integrate over A of this eigenfunction with respect to the invariant measure on the manifold. Okay, so that gives you a probability measure, since this thing is normalized to have the total space has integral 1, and of course it's a measure. It's absolutely continuous with respect to the underlying Haar measure, the underlying invariant measure. And you might want to try to understand what happens to these. So we have these measures. So we have these measures mu j, and the question in quantum ergodicity is, so each of these measures or each of these states you can interpret quantum mechanically as being the probability of being in the state corresponding to phi j. So like in chemistry, you learn about s valence and p valence electrons. So these are different energy states where you are most likely to find, this is the interpretation of quantum mechanics, is that you will most likely find the electrons in that neighborhood of the atom. Okay, does that make some sense? So so the question of quantum ergodicity is what happens to these in the high energy limit. So if this artist were to somehow pump a lot of energy into the system so that it jumps to the next energy domain, well, this is a slightly different question, because here I'm asking about what happens to the nodal regions. But at the moment, that's a slightly different question. It's related, but at the moment I want to know what happens to these measures. What happens to these eigenstates? Where do they concentrate on certain subsets of the table, or do they kind of evenly spread themselves out among the whole table? That's the basic question in quantum ergodicity. So and weak star limits, of course, means I take some observable. I just take some nice, maybe smooth, compactly supported function on the manifold, and I evaluate it. I evaluate the measure on this observable. In other words, I just integrate over the whole manifold of f d mu j. And the question is, does that converge as j goes to infinity? This convergence is as j, or rather as the eigenvalue, as the energy. So we'll order the states by the energy. As the energy goes to infinity, the question is, does this converge to the uniform measure on the manifold? And really, you want to ask this question on the unit tangent bundle, because it's also interesting to describe what happens. See, these limiting measures will be invariant to the geodesic flow, and the geodesic flow takes place on the unit tangent bundle, the circle bundle. But never mind. So that's the basic question. Is there a limiting probability measure? Well, or rather, what are the possible limiting probability measures? Presumably, the invariant measure is one of them, but could there be others? So that's getting a little ahead of myself. That's the question of quantum unique ergodicity. Quantum ergodicity just says, is it true that in the high energy limit you recover the semi-classical limit? Do you recover the uniform measure? Okay, and this was answered by Schnirelmann and many others beginning in the 70s, that if you look along a density 1 set of eigenstates, they will indeed converge to uniform measure. So almost every such weak star limit along subsequences, along almost any subsequence, will converge to uniform measure. That's the basic theorem in this subject.
So,
So far, so
Professor
good?
Kontorovich,
Please.
can I ask a question? Just so
Yes.
if I understood correctly. So if I were to take an interval for an easy case,
Yes.
if I looked for eigenvalues of the Laplacian, then I would get sine nx and Fourier basis, right?
If your manifold, well, is an
It-
interval. Yeah, here I really want at least 2 dimensions. So let's say it's a square.
Okay, but if it were the case, then you could say that, for instance, sine nx or cosine nx or e to the inx
Exactly.
would uniformly go to 0, right? In probability measure. Could I say that?
That's right.
Okay, okay, thanks.
Yes. Yeah, exactly.
Okay.
So the eigenstates here would be sine nx cos my.
Yeah.
You just separate variables when you're trying to solve the Laplacian. The Laplacian is 2 derivatives in x plus 2 derivatives in y.
Mhm.
The uniform measure is just Lebesgue.
Yeah.
And these, right, in each direction, it looks like this. And in the limit, as n gets larger and larger, it just becomes uniform measure, especially because the measure is the L2 norm squared. So the norm squared of this is just doing this.
Yes, exactly.
Great. Thank you very much.
Thanks.
Thanks for that question. Any other questions? So far, so good. Okay. So this would be the torus, and I want, really things take place in the unit tangent bundle. So I want to point and a tangent vector, and even the tangent vectors will become equidistributed, but never mind. So one reason this quantum unique ergodicity question, well, I haven't said it yet. So do we really need these subsequences? That's the question. Do we need to look along subsequences, or is it true that every large energy limit converges to uniform measure? That's kind of the basic question. And a key example, following some work of Yakov Sinai on the Sinai billiard, is Sinai student Bunimovic studied the stadium. So this has a flat part and then semicircles on the ends. And the question is, what are the eigenstates? Again, we're just solving 2 derivatives in x plus 2 derivatives in y equals lambda. And here are some eigenstates. So here are the typical, these are density plots of the eigenstates. Now you see, so there's a close connection between the dynamics of billiards on these manifolds, and I sort of hinted to it, but I don't want to get into it too much, and the Laplace question, or the Dirichlet problem. But it's easy to see that you do have a billiard. You have a periodic, you have like an entire continuum of periodic billiards that just bounce back and forth instead of ever. So if I have angle incidence equal to angle of reflection, I should typically have trajectories that do something crazy. And that's what I'm seeing in most of these trajectories. And that's Schneelmann's theorem, that these in the high energy will become uniform. But there are certain eigenstates. So this is an eigenstate I want to bring your attention to, where instead of the measure becoming uniform, it gets trapped. If I shoot it at a very small angle here, then I'll do this and I'll do something and I'll come right back. And I'll do something and I'll come right back. And the mass is not uniformly distributed. I rarely visit the ears, and I'm always in the main region. And these persist, or at least numerically they did. So Bunimovic in the 80s showed that the dynamics of billiards on the unitangent bundle of the stadium is indeed ergodic. So again, that means that's another, there are ergodic theorems that tell you almost every geodesic trajectory will equidistribute, and that's very close to showing you that large eigenvalue Laplace states will be very close to uniform measure, exactly as Schneelmann said. But this is a beautiful Annals paper from about 10 years ago. We do know that in certain configurations, in a certain sense, these scarring, so this is called scarring. These are scars because you're seeing something that deviates from uniform measure, that these scars exist. So there are, of course, sparse. There are very few of these states, but there are subsequences of states where the measure is trapped, for example, in this region. So there are infinitely many, we believe, there are infinitely many eigenstates already on the Bunimovic stadium, which have all of their mass, or 99% of their mass, concentrated in this flat part and having very little mass on the outskirts. Let me get rid of my picture so you can see the the eigenstate again. Does that make sense? Any questions on that? Okay. So scarring is real. Scarring exists, and the question. So there's some work on this in the 90s, and there was a rather bold conjecture. I mean, there was not a lot of evidence for it, and there's still perhaps now there's a little bit more evidence for it, at least in certain cases. But Rudnick and Sarnek looked at this question in the 90s and stated rather, at the time, I mean, people still argue about whether this is true or not. So this is called the quantum unique ergodicity conjecture, which says that, okay, that manifold M, the Buchner stadium, this is we have a flat metric on it. But if the manifold has negative curvature, if it's, like a hyperbolic surface, on a hyperbolic surface, the only weak star limits along any sequence, in other words, along the full sequence, is the uniform measure. In other words, the only invariant measure in this high energy limit, there's a unique ergodicity. There's a unique invariant measure of these high energy states. There is no scarring. So that is, in the quantum limit, there's a unique geodesic flow invariant measure in this limit. The conjecture, despite lots and lots of progress, and I'm going to try to tell you the progress, and actually the progress has come, the only cases in which we have any kind of serious progress are coming from number theory, and that's the interaction between our subjects. But the actual conjecture, there's not a single example of a manifold M for which this conjecture is proved. Okay, so we're still very, very much at the beginning of this story. We need lots of new ideas. But there's more that one can say if the manifold is arithmetic. So let me not go into what it means for a group to be arithmetic or for a surface to be arithmetic. But an example, a kind of key example, is the modular surface. So here H, let's go over here. H is the upper half plane, so it's a subset of complex numbers with imaginary part positive. Okay, so if this is the complex plane, this part is H. H can be turned into a hyperbolic space. Probably you're all familiar with this, but hopefully I'm not boring you too much. So if you put a Riemannian metric where the measure of a little region is dx dy over y squared, now you have constant curvature -1. This will have constant curvature -1. Now that space is way too big. That's just we want something smaller, not necessarily compact, but at least a finite volume manifold, so that we can speak of uniform measure. So uniform measure, so there is a probability measure, a flat probability measure. So we take some subgroups. So there's a group, the group SL2R is the group of isometries. So these are 2x2 matrices, A, B, C, D, in 2x2 matrices with real entries. So A, B, C, D are real. And the linear action needs to be invertible. So AD minus B, the determinant AD minus BC needs to be non-zero. And the special linear group is that where it's not only non-zero, but it's normalized to be 1. So these are determinant 1 matrices, determinant 1 2x2 matrices. And the action of this, so there's a sort of standard theorem that the isometries, or at least the orientation preserving isometries of the upper half plane are in one-to-one correspondence with, well, PSL2R, but never mind. You have to mod out the negative identity matrix acts trivially. So, all right, I'll put it there, but don't worry about that too much. So this acts on hyperbolic space. And let me just see if I'm completely boring you. Does everyone know what the action is? What I'm about to write down for what the action is? So most people do, but maybe not everybody. So you take a point Z, and it maps to AZ plus B. This is the fractional linear map, fractional linear transformation, fractional linear transformation. Okay, which you can reinterpret as acting on projective points. So, and anyway, there's a very natural place where this transformation comes from. And so if you take this group SL2R, in fact, let me go over here. So SL2R acts transitively on the upper half plane. In other words, for any point, so there exists a matrix G in our big group G. G is SL2R. There exists a G and G. So for any Z and W in upper half plane, can you see where I'm writing here, or should I make it a little bigger?
Maybe a little bit bigger.
A little bigger. Let's try again. Let's try again. You know what? Let me add a page so I can, how do I add a page? Does anybody know? I thought I knew how to do this. Add a page. There we go. Great. Okay. Now we have room to work. So we have G in G. G is SL2R. And what I'm saying, my claim, is that the isometry group SL2R acts transitively on H. And so what I mean by that is for any 2 points Z and W in H, so I have some Z and some W, there does exist a matrix in SL2R that maps Z to W. Okay, so the action is transitive. And the stabilizer, so we may as well choose some nice point. It turns out that I is a nice point. It's sort of the center of the upper half plane in some sense. I mean, any point can be taken to be the center. It's like, what's the center of the real plane? Well, the origin, but any point can serve as the origin. It's all the same. The stabilizer of I in G, one can work this out. It's a fun computation. It's that it's SO2. Okay, so this is the group. If you are familiar with, you're probably familiar with these things. I think they arise in physics all over the place. But in fact, this is the circle bundle. This is the tangent direction. So we can identify the upper half plane with SL2R mod SO2. So far, so good. And then we can look at discrete subgroups. So given a discrete subgroup, gamma in G, for example, SL2Z. SL2Z, which is same thing, 2 by 2 integer matrices. So now integer matrices, integer entries with determinant AD minus BC equals 1. Okay, maybe this is completely familiar to all of you. But this is a nice arithmetic group because it's defined. I mean, what makes this an arithmetic group is that there's an algebraic variety, AD minus BC equals 1. And whenever you solve this variety, so the integer points of this variety are exactly the points of this matrix group. And there's a group action on the points of this variety. So anyway, that's just for your general knowledge. So you can take the upper half plane and mod out by the action of SL2Z, and you'll get what's called the modular surface. It's the moduli space of elliptic curves, in fact, or twice, lattices in the plane up to homothety. So then unimodular lattices. Then one can exploit. So if you have an arithmetic lattice, if you have an arithmetic surface, a surface that's a quotient by an arithmetic group, then one has extra symmetries. And these are the so-called Heka operators. They're these hidden symmetries of the space. And one can try to exploit those extra symmetries. So let me,
Sorry.
any questions? Yes.
Yes, these extra symmetries, why does it pop up? Does it, like, did we have them starting from H? Maybe when you quotient out, they inherited these symmetries because of H has certain symmetries, maybe?
That's a great question. It makes complete sense. And in fact, people didn't really understand. So Heka observed these symmetries. That's why they're called Heka operators. And he even studied to what extent they exist on other kinds of quotients for groups, for non-arithmetic groups. And it turns out that there are no Heka operators for general groups. So general discrete groups, even groups of finite covolume. So that was the next thing I was going to say. So a fundamental domain for this action, a fundamental domain is for H mod this group gamma SL2Z. There's a standard version. I mean, there's uncountably many domains one could write down. But what I mean is an open region so that any point in space, any Z in H, can be mapped into some fundamental region, and or at least its closure, and any 2 points inside the region are inequivalent under this transformation gamma. So a fundamental domain is the set of points Z in the upper half plane. So a fundamental domain for gamma, let's call it F, is the set of points so that the real part is between -1/2 and 1/2. And hopefully it's clear why these two geodesics are boundaries of a fundamental domain, because inside this group SL2Z, there's a matrix 1, 1, 0, 1. And what it does under fractional linear transformations, so 1, 1, 0, 1 of Z, let's see how, yeah, okay, so everybody knows it's Z plus 1 over 0 Z plus 1. In other words, it's just Z plus 1. It's translation. So you can translate by 1 to the left or right as much as you want. So wherever your point was, if I have a point over here, I can move it by 1, I can move it by 1, move it by 1, until the real part's between -1/2 and 1/2. There's another matrix in SL2Z, which is the matrix 0, 1, -1, 0. I'll leave it as an exercise that what this does, well, it's sort of an immediate exercise. What it does is it sends Z to -1 over Z. So this is reflection through the unit circle, but reflections are orientation reversing. So we reflect through the unit circle, and then we reflect through the Y axis. And those two together are orientation preserving, and that's what this transformation does. And when you do that reflection, the imaginary part always gets larger. And the group acts discretely. So in fact, this is a fundamental domain. So we can always get outside of the unit circle. So the absolute value of Z is greater than 1. So that's kind of the standard fundamental domain for this quotient. So it's this fundamental domain that has those symmetries. But you could take another group. So just to give you one more example, here's another Heka triangle group. The 2, 5, infinity Heka triangle group is the same idea. It's the group generated by inversion, 0, -1, 1, 0. So that's inversion in the unit circle. But instead of translating by 1, I translate by cosine of 2 pi over 5. So if I take this group, that's the Heka triangle group with one angle is pi over 2, and then another angle is pi over 5. So this angle is pi over 5, and then the last angle is 0. So that's this 2, 5, infinity triangle group, which this is acting by reflections, and we want the orientation preserving double cover of it. So that's what this group is. And this group is non-arithmetic, and it does not have the Heka symmetries that are. So it's really the arithmetic that gives you these extra symmetries. That's what I wanted to emphasize.
Thank you.
Of course. So here's the modular surface. Let me zoom back in. So now we're talking about arithmetic quantum unique ergodicity. So you look at the modular surface. There's an invariant Haar measure, as we've said already. The Laplacian, I didn't tell you what the Laplacian is in these coordinates. It's the Euclidean Laplacian times y squared, in the same way that the metric, that the measure is Euclidean measure divided by y squared. And here are some large eigenvalue eigenstates. So these are density plots of these eigenstates. In this subject, these eigenstates are called Moss forms. So again, this is the fundamental domain. And on each of these fundamental domains, I mean, it's not so obvious where the symmetries are. There's an obvious symmetry, reflective symmetry about the y-axis, about the central line. But then you can sort of see some other symmetries, and these extra symmetries are the Heka operators. It'll take me a little too long to say exactly what they are, but they're there. So for every prime p, in fact, for every integer, but never mind, for every prime, there is another operator called TP, the pth Heka operator. And the amazing thing about these operators is that they all commute with each other, and they commute with the Laplacian. And so when you look, if you're trying to decompose, you have your L2 of the manifold, and you let the Laplacian act, and you want to decompose this into irreducible components, right? Lambda eigenspaces over lambda. In fact, there's also continuous spectrum. There's not just discrete spectrum, there's plus continuous spectrum. Continuous spectrum from the fact that this quotient is non-compact. So this quotient is finite volume. So the fact that that's finite, well, you have to compute what happens to this bit of, it's obviously finite in this compact part, but this part, well, 1 over y squared is integrable. And so the volume turns out to be finite, but it's non-compact. Finite volume, non-compact. So the non-compactness causes there to be continuous spectrum. And in addition to the continuous spectrum, there does exist discrete spectrum, although that's also something very special to arithmetic groups, which is proved from Selberg's trace formula. There's a Weyl law for how many of these discrete eigenvalues of the Laplacian actually exist on this space. And the preponderance of most of the spectrum is this discrete spectrum, unlike the non-arithmetic setting, where it's the exact opposite. There's also continuous spectrum, and it seems like the discrete spectrum is either only a much lower order or completely non-existent, depending on the setting. Okay, so we have these other symmetries, these Heka operators, and one can decompose the eigenspaces. Because the operators commute, we can take simultaneous eigenstates, simultaneous eigenfunctions of the Laplacian and all of the Heka operators, and that will give us what are known as Heka Moss forms. I realize I haven't told you what these Heka operators are, but do you sort of still see the basic ideas? You were sort of, if these lambda spaces have large multiplicity, then there's no particular choice. If these have large multiplicity, then I'm kind of in trouble for the quantum unique ergodicity conjecture, especially if the multiplicity can grow, because then in these spaces, I can choose linear combinations of the invariant states. There's no other way to distinguish the states as they occur in these subspaces. If there's a large multiplicity if there's a sequence of eigenvalues with larger and larger multiplicities, then I have more and more room to try to create scarring, to try to create these non-equidistributing states. We can create scarring, can see scarring, can potentially at least see scarring. But the amazing thing is, right, so first of all, conjecturally that doesn't happen. Conjecturally, the Laplace spectrum, at least for the modular surface, is already simple. And so every Moss form is automatically a Heka form. This is wide open. We have absolutely no idea how to show this. But, I mean, we want to prove a theorem. So we will, if there is any multiplicity, when you take simultaneous eigenfunctions of the Heka operators and the Laplacian, now there's a multiplicity 1 phenomenon. In fact, the eigenvalues of the Heka operators are themselves the Fourier coefficients of these Moss forms. And so if all of the eigenvalues are the same, well, all the Fourier coefficients are the same, so the functions are the same. So I gave you a sketch of the proof of multiplicity 1. So basically, we can break down this space into one-dimensional subspaces. So now we genuinely have these sequences, which is what we were looking at in the first place. Okay. So if we want to show equidistribution, Hermann Weyl gave sort of a prototypical way of showing equidistribution, which is to show that you have cancellation along any non-trivial eigenstate. So in fact, if you want to prove, so we want to show that mu j of f of any test vector converges to uniform measure. So the Weyl criterion is that it's enough not to take arbitrary test vectors, but to take eigenstates themselves. Take f itself to be an eigenstate with a different eigenvalue, with not necessarily the same eigen, with some fixed eigenstate. So you fix an eigenstate f. F is a fixed Heka Mass form, and integrated against mu j. Again, that's just norm phi j squared against uniform measure. Okay, so far so good? Ish. Well, I only have 4 minutes left, so I'll try to say something in the remaining couple of minutes that maybe won't lose too many of you. So it's enough to take f to be a fixed eigenstate. You also have to deal with the continuous spectrum, but never mind. And you want to understand whether this goes to 0 as j goes to infinity. You see, the constant function, so basically we're decomposing the space. If we want to know that this is true for any test vector, we want to know that it's true for the constant function and any eigenfunction, because everything else will be linear combinations of those things. And for the constant function, of course, this is always 1. So you have the measures are probability measures. So what we want is that's the only thing that survives. So for all of the other states, if f is anything but the constant function, if it's a either in the continuous spectrum, which is spanned by something called Eisenstein series, or it's one of our Heka Mass forms, we want to know that this triple product converges to 0. Now there's an amazing formula called Watson's formula, which says that if you have 3 Heka Mass forms and you take their triple integral like this, what you get is a triple product L function. So this is a degree 8 L function. In fact, you get a central value up to all kinds of other factors like gamma factors and symmetric square factors and so on. So I just want to very quickly show you why or what this is, maybe. So what's an L function? Let's go all the way back. Maybe you've seen the classical Riemann zeta function. Of course, this is a Dirichlet series. A Dirichlet series is some coefficients over n to the s. So it's a Dirichlet series defined by Euler, which we call the Riemann zeta function. Of course, there's good reason for all of these different names. But there's an Euler product formula. So the sum over, this is if the real part of s is bigger than 1, then this converges absolutely and is equal to a product over all primes of 1 over p to the s, 1 minus 1 over p to the s, all inverse. And the reason it's called the Riemann zeta function and not Euler or Dirichlet is that Riemann gave a meromorphic continuation to all complex numbers. There's a simple pole at s equals 1. And when s is 1, we get the harmonic series, 1 over 1 plus 1 over 2 and so on. That diverges, nothing you can do about that. But everywhere else, you can define an analytic continuation of this. And that analytic continuation has a functional equation that sends s to 1 minus s. That analytic continuation has zeros in the critical strip. So here's the complex plane. Here's 1. Here's 0. So we know that there are no zeros here because this infinite product converges absolutely, and none of the terms are 0. So here the zeta function is not 0. Here the zeta function is basically non-zero. There's some trivial zeros that arise from the gamma function. And then this is the big, the literally $1 million problem, is what's going on inside of this region. That's called the critical strip, where the real part of S is between 0 and 1. And the Riemann hypothesis would say that all of the zeros lie on this central axis of symmetry. Remember, we have a functional equation, S goes to 1 minus S. Now, the Riemann hypothesis, so there's something called the Fragment-Lindelof convexity principle, which says, this uses Stirling's asymptotic formula for the gamma function, which says that as you go up this central line, so if you look at zeta at some a half plus it for large t, this grows no faster than t to the 1/4. That's what we can prove. But actually, the Riemann hypothesis would imply something called the Lindelof hypothesis. The Lindelof hypothesis says that, in fact, zeta of a half plus it doesn't grow like t to the 1/4 plus epsilon. It grows like t to the epsilon. So there should not be this 1/4. And we say we have a subconvex bound for the zeta function if you can get an estimate for the growth rate in t on the central line that's anything slower than this convexity bound 1/4. And this was first done by Hermann Weyl in the case of the Riemann zeta function. Okay, does that make at least some sense? Well, we're almost done. These for Heka Mass forms, they also have L functions. These L functions are degree 2, so they have 2 Euler factors. And that triple product L function that I mentioned has 8 Euler factors. And if F has Euler factors alpha and G has factors beta and H has factors gamma, then their triple product is just multiply all possible combinations. So that's why there are 8 things here, and multiply this over all the primes. And it turns out that will be a nice L function. And in the end, what you get is that if you measure this eigenstate on this, so this again is mu j of f, which is the triple integral, exactly as we discussed. Watson's formula tells you that that's related to the central value of this L function. And if you use the Fragment-Lindelof convexity bound in the parameter that the j is growing, so or lambda j, the eigenvalue is growing, what you get proves that this is bounded by eigenvalue to the epsilon. But of course, we want it going to 0, not possibly growing, but going to 0. And what one needs is any subconvex bound for this central L value, because it's evaluated at a half. That's exactly the center of the critical strip. And no such subconvexity for a degree 8 L function is known today. But there is progress, and this is breakthrough work of Elon Lindenstrauss, based on work of many others, Luo Sarnak and Jacobson, who handled the discrete spectrum. There's a paper of Lindenstrauss and Bergan that was instrumental in Lindenstrauss's work, and Sander Arjun to finish off a potential escape of mass. But Elon Lindenstrauss developed tools from measure rigidity, ideas from Furstenberg's 2x3 conjecture, whatever that is, to use these Heka operators on p-adic spaces, on S-arithmetic groups, to finally settle the arithmetic quantum unique ergodicity, for which he won the Fields Medal in about 10 years ago. So at least along these Heka eigenstates, there is no scarring in this context, but much more work remains to be done, and maybe that's where you come in. So thank you for your attention. I'll stop there.
Well, thank you for this wonderful talk, and thank you so much for accepting our invitation. So are there any questions?
I can ask one.
Please.
Sure.
Or a few, actually, but simple ones, because first of all, I missed why you called this quantum. Is it because you were working with the Laplacian and on a complex plane, or some submanifold of complex plane?
No, it's it's that quantum mechanically we have discrete states.
Yes.
At which these exist.
Yes.
With larger and larger. So the quantum is that we've discretized
Yes.
the energy states, and then we're taking a high energy limit.
Because of the discrete spectrum, then.
Yes.
Okay. No. All right. So what is the implication of scarring phenomenon to physics then?
Well, yeah, that's a good question. I guess if there is scarring, so if we think back to the chemistry, S valence, p valence, and so on, electrons, if there's scarring, then along certain subsequences of energy, electrons can only be in a particular space, in a particular area, and not in the high energy getting completely equidistributed anywhere around the atom.
And if I understood correctly, so you have a limiting process, right? Does this happen for a single physical system? In your case, if we were to consider a physical system, does this make sense? So you take a physical system, then you look at its spectrum. Then you have these eigenvalues and eigenfunctions of your Schrödinger's operator, whatever it is. And you're taking the limit of these measures that are given to you by these certain eigenfunctions, I guess.
Yes.
So you have a single physical system, and what you're saying is, if you have scarring, then you have some sort of localization for certain states.
For certain, yes, exactly. There are special states that are thin in the set of all states. For almost all states, it's becoming equidistributed, but there are certain rare states where if you could somehow tune your eigenstates to only hit those states, you tune your energy levels to only hit those states, the electrons would stay in some fixed region and not spread out all over space.
So this goes against somewhat to the spirit of correspondence principle, you can say. So if you take,
yes, well,
if you tune it well.
I guess so, yeah.
All right, thanks.
In fact, maybe it would be great if there were scarring, because then maybe there could be some engineering applications. I don't know.
Okay. Yeah.
Okay. You could
Thanks.
localize, well, of course you can't localize position and momentum, right?
Yeah, but maybe if you need just one of them.
Right.
Thank you very much.
Yes, there is another question from Sesim.
Yes. Hi, Alex. Interesting talk. I'm a physicist, and I like to, could you comment on a little bit this scarring phenomenon and the chaotic dynamics? Because you show us this Nye billiard model, and those models were studied heavily by the physicists alike. And as far as I remember, in that system, for some specific phase space parameters, the system behaves chaotically. So if you just start integrating the equations of motions, geodesics does not cover all the space, they're confined in one place. The motion is not quasi-periodic, but it becomes chaotic in a sense. So is it like a common feature that as far as the quantum mechanics concerned, if I have a chaotic system at hand, does it necessarily imply quantum scaring as well? I can't pronounce that, but anyways.
So let me try to understand your question. If you have that was the basic question. Is being chaotic, is the ergodicity of the dynamics, does that imply that there does not exist scarring?
Or the exact opposite.
Yes. Well, I guess initially people maybe thought that ergodicity would rule out scars, but so your question is it true? Well, what quantum unique ergodicity says is it's not enough to have chaotic dynamics. You need chaotic dynamics and negative curvature.
For scarring to happen.
For scarring not to happen.
Not to happen. Okay. For
scarring not to happen. So if you have chaotic dynamics and negative curvature, actually negative curvature already tells you the dynamics is chaotic. If you have negative curvature, then first of all, the dynamics is chaotic. The trajectories are act ergodically. And at least that's the conjecture. There is no scarring, does not exist. So if you are looking for scarring, the best place to look is in the flat metric, not in hyperbolic metrics. So if you're looking for potential counterexamples to quantum unique ergodicity, of course, then go look in hyperbolic spaces. So I think there's still great debate. I don't think people are settled on the quantum unique ergodicity question. People are still arguing about whether it's true. But for these arithmetic manifolds, and as long as you allow me to decompose things not only by the Laplacian but also by these Heka operators, then we know that there is no scarring.
Okay, thanks.
Did I answer your question?
Yeah, that cleared up a little bit. Yeah.
Are there any questions?
I have one.
Please.
By the way, thank you for your great talk. First of all, I want to ask something about the Heka operators. Now, we equate the upper half plane by taking the quotient of SL2R with the stabilizer group.
Yes.
Then we take one more quotient with the discrete SL2.
Yes.
SL2Z, and then by these Heka operators, we get some extra symmetries in our system. Now, in string theory, we have a similar construction. I will ask that if it's related or not. We take ODD Lie group as instead of SL2R.
Yes.
Then we take the quotient by the stabilizer OD times OD.
So maximal compact.
Yes, and then we take one more quotient by ODD, but now in integers.
Perfect.
And this exactly the match with the modular surface and this space.
Absolutely. And the Langland's, yeah, go on.
And because we are doing string theory, we get some extra symmetries like T duality. It's not present in the particle case. So my question is that this T duality or other dualities of string theories are related with the Heka operators or not?
Well, so I'm far from an expert on string theory, but I will just say that there is so there's a Langland's program, which tries to understand L2 of. I mean, we don't even need this. Just what can we say about decomposition of such quotients, exactly as you said. So we have some Lie group. We quotient out by a discrete subgroup. In general, we do this adelically. And my understanding is that physicists, so I guess Witten and lots of people have been thinking about what these have to do with string theory. The functoriality, I think, is the closest thing to. I'm told that functoriality is related to supersymmetry. Functoriality. So functoriality, actually, what we saw, by the way, what we saw with this degree 8 L function is an instance of functoriality. This is supposed to be the GL2 cross GL2 cross GL2 into GL6 lift, GL8 rather, GL8 lift. It's a triple product conjectural Langland's lift. So what that says is does there exist an automorphic representation in L2 of GL8R mod GL8Z so that the L function of that automorphic representation is exactly this L function. So we can construct an automorphic form that has this L function, and the question is it actually invariant under all of GL8? So there should be more functional equations than those that we see from the setup alone. And so this massive program will prove things like the Ramanujan conjectures, the generalized Ramanujan conjectures, and Sato-Tate and things like this. So I'm not sure I directly answered your question because I am not competent in string theory and supersymmetry, but I'm telling you the words that I hear people say that are related to things that I understand.
Good. Thank you. I will check the Langlands program and functionality. Thank you.
Okay, thank you again. Is there any question? Maybe one last question, because we have another talk.
Hello, I have a quick question. First of all, thank you very much for your talk. I wonder what is the work? I mean, could you briefly summarize the work on the p-adic Heka operators on p-adic spaces? And this might be a stupid question, but if it somehow connects to p-adic L functions, I wondered. Thank you very much.
Yeah, thanks for the question. So this particular work is not so much about p-adic L functions. That's a slightly different setting. But one of the key ideas here is that instead of just looking at SL2R mod SL2Z, one can look at SL2R times SL2QP, the p-adic number. So this is an S arithmetic group. And then one can quotient out by SL2Z adjoin 1 over P, which will be a discrete group when embedded diagonally in the product. And so it's these kinds of spaces on which we have a pair of operators, TP and delta, acting individually. Each of these acts on this quotient. And that's the sense in which it's a ×2 ×3 type phenomenon. So Furstenberg's conjecture is that the measures, if you have a measure on the circle, which is invariant under multiplication by 2, and it's invariant under multiplication by 3, and it's ergodic, then it's Lebesgue measure, and it's uniform measure. So it's having this higher rank, having access to a higher number of invariant operators that allows for something like measure rigidity. So that's the sense in which, if you just look at SL2R by itself, it's very hard to see. I mean, as another question asked, do we always have Heka operators? No, we don't. But if you look at these S arithmetic quotients, which by the way are, I mean, this can be reinterpreted as SL2R, as the modular surface itself, SL2R mod SL2Z. I mean, this quotient has is some fancy way of capturing the p-adic dynamics. And the p-adic Heka operator is the same thing as geodesic flow. I mean, yeah, it's the p-adic Heka operator is the p-adic analog of geodesic flow. And so that's what's being exploited in this work. I hope I answered your question.
Thank you very much. Thank you very much for the answer.
Okay, thank you, sir, again. We are very happy to see you here today. And also you are very welcome to come to Turkey. I hope we see there. We see here.